Yeah, that may be the problem. So I discovered this after class on Tuesday that the values that I have in the spreadsheet somehow do not match what your output is giving in the information. They're off by one.
Oh,
And
like up one or down one?
mine are low by one for the
So
information.
I would have for the information. So I
Yeah,
would just subtract one from all of my information values to match what you have in your.
I believe that would be correct. If you just use what I gave you, then you should get the right answers because that's what I had intended because not everybody has access to the plotting features in M+. People who are using it on a Mac, for instance, do not. And so that's why I had done it for you. But that was a column that apparently I had forgotten to update relative to a previous version of the assignment. So my numbers aren't going to match yours.
Maybe I should clarify because what I did was, so for the binary test information tab, I added an extra column and titled it reliability. And what I did was took the binary test information column divided by 1 plus the binary test information column and then just dragged it down to get a value for every single theta.
Okay,
And then that way that should have worked.
that should have worked.
It didn't though. So I didn't know if I should.
Okay. I may have to look at that since that's a more specific question. But
Okay.
what I was talking about is if you went to the trouble to build your own test information column, then the one that comes out of your numbers is not going to match the one I gave you. I just discovered that on Tuesday. But if you use the one I gave you, then it should be okay.
I guess maybe I did the wrong thing. I'll ask you after class because maybe I'm using the wrong values.
Possibly, yeah. But otherwise, that is correct. To get from information to reliability, it's information divided by information plus 1. Make sure you
Was
have
M plus
parentheses, by
not?
the way, on the
I
denominator.
did, yeah.
Okay.
Yeah. For M plus, when it spits out the data for you, since it doesn't have anything labeled, I kind of had to guess what it was, and had it in I opened it in Notepad and then I copied and pasted it into Excel because I was having problems with the import thing. But anyway, those two columns that it gives you, is that the theta value and the binary test information values, or because that might be why it's wrong too.
Um, yes. So at the very bottom of your output, it tells you the names of the columns in the order of whatever files that it creates. So like if you ask for factor scores, you'll get a listing of what the columns mean in the outputted data set. But for this, I hadn't intended that you actually get a data set that has information saved to it. So if that's what you were doing, then that's what I'm talking about as not matching. I had intended for you just to use what I gave you as output in the Excel sheet.
Okay, I'm still confused, so I'll ask you later.
Fair enough. Okay. We've still got folks trickling in here. So homework questions, homework 4 while we're on the topic. Anybody else want to play?
I have a question about diff thing.
Okay.
So I understood that the smaller sample size is better for having the result I want, which is two models are similar.
Yes, you have less power to detect differences in parameters if you have fewer people. That is correct.
So is there any kind of appropriate size? I mean, the least amount of size for doing that analysis?
There's not really any hard and fast guidelines. It's a continuous function of effect size and sample size, the same as it always is, right? If you have very large differences in your item parameters, it takes fewer people to detect them reliably. So it just depends on how big the problem is, so to speak, how many items you have, how close together the item parameters are, and how many people you have in each group. If you have a group that is small relative to a group that is large, that's also somewhat problematic because the parameters are going to be more unstable. They'll have larger standard errors in the group that's small. So I would say give it a try, see what happens, and try to pay attention to how big in an absolute sense the differences between the parameters are, in addition to just the size of the significance tests.
So there is no kind of exact size, I mean, exact number for size. However,
No.
it would be better to have balanced number between groups. Okay.
Yes. If possible, balance is better, but I wouldn't recommend throwing away people to get to balanced. I would keep
Okay.
all the data that you have.
Okay. Thank you.
Sure. All right, I just started sharing. I think I've got the recording going. Yes, we do. So we're talking about invariance in diff. So if there's no more homework questions for right now, we can segue into that. So tell me, what is invariance all about? What's the point? Why would one want to do an invariance analysis?
To see if the items perform similarly across different groups of people.
Yeah, that's one instance. So item parameters specifically, so how the items relate to the latent traits via their factor loadings, their intercepts, and their residual variances in CFA, or via their loadings thresholds in IFA. Yeah, I'll take that. Chat window to tell us whether or not the items measure the same latent trait across groups or across time. Yes. So I'm using groups in sort of a generic case, but anytime you have more than one measurement and you want to see whether or not the items are measuring the trait the same way. So it could be across distinct groups of people, it could be across repeated conditions, it could be a self-report form versus an other report form, something like that. So anytime the same item is, you have multiple measurements on it. And to test the equivalence. So if something is invariant, that means it is the same. If something is non-invariant, that means it is different. And in the same models in the context of IRT or IFA, the phrasing is opposite. So we talk about needing to do tests of differential item functioning, which is the same thing as measurement non-invariance. So diff, as it is abbreviated in that context. But yeah, anytime that you're looking to make sure that your trait is comparable in its measurement across different samples or different occasions, something like that, we got to do invariance. So even if you think about just your classic, two-group t-test, right? Have you ever run an analysis on a sum score and looked at mean differences between two groups? That's one of the first things they teach you how to do in intro stat, right? I've got an outcome. I've got two groups. I'm going to compute my t and see if their means are different. That presupposes measurement invariance. It presupposes that the way those items relate to the trait they're supposed to be measuring, not only do they do so to the same extent, but they do so equally to the same extent across groups. So this is one of those topics where you're assuming measurement invariance a whole lot of the time. For those of you who want to come learn how to do longitudinal models with me in the spring, is anybody going to come play? Yeah, I'm going to assume measurement invariance the whole time because I don't have time to talk about that. So anytime you do a growth curve analysis, you look at the extent to which an outcome changes over time. You are presupposing that the way that the items relate to the trait that they measure is the same across time. So this shows up a lot as an assumption that we don't even think about. There are ways to combine growth modeling for change over time with tests of measurement invariance, and that is actually the background of example 7b that I have for you that was posted for today, which we may or may not get to today. So we'll get to talk a little bit more about that context. All right, so in these models, there are particular terms that describe the stages of the analysis. And where we were last time is talking about configural models and then metric invariance models, right? So configural. what happens in a configural invariance model? The best it can ever get. Yeah, have we made any sort of constraints across groups at all in the configural invariance model? No. We're letting all parameters differ across groups that possibly can, but we're estimating the model simultaneously. So it's a separate but simultaneous set of parameters. So for instance, we were looking at this example. This is a CFA example. So we're pretending that this 9-point ordinal scale is sufficiently continuous to have a linear model of a depression trait predicting each of these 9 responses. We're looking at how these items measure depression across women and men. So in this case, women are the reference group and men are the alternative group. And so the code looks like this. Here is the new part with respect to the input. So on variable, you have to tell it which variable in your data set controls which group someone is in and what the labels are. And then after that, you have a general model statement like usual. That is going to describe what the factor model looks like specifically in the reference group. So in the 0 group for the women here. And then you're going to have another model statement that has the alternative group's label after it. This one does not turn blue, by the way. This describes how the factor model needs to differ in the alternative group. And so the code to set the factor model for these 9 items, for instance, I do not have the same label on anything yet. So I've got L1 through L9 as a label for the women. I do not have it for the men. Likewise, I've got a label I1 through I9 for the women. I do not have it for the men. So what's going to happen in my code is that this whole side right here, that's going to stay the same in this entire example. It's not going to change. In the reference group, I have a model in which the factor mean is fixed to 0 and the factor variance is fixed to 1 for identification. And I have then estimated all item intercepts, all item loadings, and all item residual variances. I have labeled every term in the model that is estimated. So this code on the left is going to remain unchanged as we progress through the models. What's going to change is how we say the model for the men gets to differ from the model for the women. Right now, everything gets to differ. And I had a question after class, why do I have a residual covariance for item 1 with item 2? It's because the author said I needed one. So this is the example that he goes over in your textbook, and the invariance analysis follows after an example where he goes through to figure out what the one factor model needs to look like, and they determine that you need this extra covariance in there. So for reasons already discussed is why. So then we get one set of fit statistics, okay? So this is a joint test of how well the single factor model fits each group separately but simultaneously. So it's the mismatch again between the covariances between the items as they are in the data. So as they are in the H1 perfect model relative to what our single factor model predicts the covariances between the items should be, which is summarized in terms of the height of our HO, our separate model. So there's only one HO model that's describing simultaneously the fit of the model to the women and the fit of the model to the men. And as we said before, this is as good as it's going to get. So even though we don't have perfect fit, our chi-square test of how much shorter our HO model is than the H1 model is significant. The rest of the fit statistics look pretty good, so we can proceed with this as a reasonable starting point. And I made a picture for you of what the loadings look like out of this configural model. So here is the solution for the two groups. So the solution for the women is shown on the left. The solution for the men is shown on the right. And let me point out the scaling of the model here. both groups have a factor mean of 0. So these two groups are not relatable to each other at all yet. They're not linked together. Each of them, it's like you've standardized within group. So I can't say anything about whether men have more depression than women, or whether men are more variable in their depression than women. I can't say any of that yet because they're not linked together. It's separate. The other thing that is noteworthy is that for invariance analysis, we are focusing only on the unstandardized solution because we want to make sure that the absolute regression model that's describing the original data is what's being compared across groups. So we're going to put the constraints on the unstandardized loadings, on the unstandardized intercepts, on the unstandardized residual variances. So even if we make, say, these sets of loadings the same, the standardized versions of the loadings will still differ. So we're focusing only on the unstandardized solution. Okay, are you ready to do this? So our objective then is to see how much of the model we can force to be the same across groups without hurting fit. So every hypothesis test from this point forward, our hope is that if it's the same across groups, it should be non-significant, which means the model is not worse. If the hypothesis test after putting the constraints on is significant, that means we shouldn't have constrained it. And so we need to figure out which parameters need to be different in order for the fit to be satisfactory. And the idea that some of the parameters could be the same, but some of them need to be free to differ between groups, that's known as partial invariance. So it doesn't have to be all or nothing, and most of the time it won't be. All right, questions before we dive back in? Okay, can you guys see this okay, or do you want me to zoom in further? It's okay to have the two columns like this? Okay, because I see some of you like leaning in and squinting, and that seems like that might hurt your eyes, so. All right, then the first thing we're going to test, metric invariance is the next step. And this is the idea that the only reason why the factor loadings differed between groups is because of differences in factor variance. So we let there be differences in factor variance. We force all of the loadings to be the same across groups. And this metric invariance phase is also known as weak invariance. So you'll see people use that terminology as well. So here is, as I said, the left-hand side, this is the same. Left-hand side is going to stay the same. I'm just repeating it for reference. So the model for the women looks exactly the same. The model for the men has changed in two places, right here and right there. So on the by statement, we have picked up the labels that were being used on the women's side and added them to the men's side. So not only are these labels, these are now constraints. I am saying that L1 on the left-hand side is going to have to be the same L1 on the right-hand side. And L1 refers to the loading for item 1. L2, which is implied by the L1-L9, refers to the loading for item 2. So we still have 9 loadings. This is not a tau equivalent Roche model thing, right? Each item gets to have its own loading. What we're saying is that item 1 has the same loading across groups. Item 2 has the same loading across groups. And so because we constrain the loadings to be the same, we have to free the factor variance in the alternative group. So I'm putting a star there on the factor variance to free it, as opposed to the factor variance being fixed at 1. So now the two groups are sharing identification with respect to the loadings and variance. They are on the same scale with respect to their factor variability. So if this factor variance were estimated to be a number that's greater than 1, I could infer that men are more variable in their latent traits than women. And if the factor variance were estimated as less than 1, I could infer that men are less variable. So we can make group comparisons now with respect to the loadings and factor variances because of these additional constraints. Okay, are you with me? Question, what does it mean that you still have the mean of 0 for the male group? Great question. I have to still have the factor mean fixed to 0 because I haven't yet put any constraints on the intercepts. They are separate. So when you're working with data that are characterized by a normal distribution, the parameters that go into making a mean are estimated separately than the parameters that go into making a variance. They don't have any correspondence in this distribution. So if I'm fixing things with respect to the loadings and the variance, that says nothing about the other side of the model, which is the means and the intercepts. So the groups are on the same scale with respect to the loadings and factor variance. They are not on the same scale yet. There's no tie between them with respect to the intercepts and the factor means. That's coming. That's the next step, but we're not there yet.
So if you made the variance for the women something other than 1, would that also, like let's say you made it 2, would that also increase the now freely estimated factor variance for the men?
It would be relative to 2.
Okay.
Yeah, so you can think like it would, if they're more, then it would have to become 3 or something. Yeah, and that's a good point. I could do whatever I wanted in terms of the at sign here because it's you're setting the key of the model, so to speak, right? What everything is relative to. So I will tell you, I think this is in the slides, but this seems like a good time to bring it up. The way that I am teaching you to do this is somewhat atypical. I can't remember what he does in the book, but a lot of times what people will do instead of this is the method of identification where the first loading is fixed to 1, and then the factor variance is free in both groups. Now, why do you think I'm not doing it that way? Any guesses? Let me back up. Do you know what I'm talking about? Let me borrow some code and open up a new window here to type to so that I don't screw up what I've got. Okay, so in the women group, this is what I've currently done. And that's in the women group. And if I go down here and in the men alternative group, I've done this. What I'm saying, this is what I'm doing relative to an alternative, which would be this. Set that equal to 1. Item 2. That means that I can then estimate my factor variance. And I would have to do the same thing here. Okay, let me divide this up here. Okay, so I'm doing it the top way. The bottom way is more common, but I believe mistaken. So guesses as to what the difference would be and when one way would make a difference as to which you used. It's no longer on a z-score metric. That is true, but not my motivating factor in this case. Another guessing because you are interested in variability across groups as a whole rather than in one loadings. Not following that guess. The second code is based on item 1, but item 1 can be different based on groups. Yes, ding, 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 ding. 1 and 1. These ones are here, not because I'm saying that the item is invariant, but because that's how I'm identifying the model. But what if I'm wrong? What if the loading in the men is like half as big as in the women? Could that happen? Sure it could. And if I've anchored this whole solution by making these things both equal to 1 when they actually shouldn't be, everything else is screwed up. So that's why I'm not doing it this way. The benefit of the specification that I'm using up here is that we can test all 9 items loading simultaneously. The model is still identified jointly between groups because of depression's variance being at 1 in the women. So this is why I'm doing it this way. There are a couple of references that I could give you if anyone ever hassles you about this, as to people actually went to the trouble to show that 1 has to be 1, that if you set it the marker as 1, that's an invariance constraint that you didn't intend. So it's not really new information, but it is a less common way of approaching the problem. So this is what I would recommend. Fixing the factor variance at 1 in the reference group allows you to test all the loadings and not have any of them fixed for identification that could actually need to be invariant. So,
Was the reasoning you said it was because item 1 might not be the same in each group? Is that saying like you gave them, okay, forms that the items are in different orders?
not physically which item is item 1, but just the idea that item 1 could be less related to the trait in one group than the other.
I see what you're saying. Okay.
Because in the previous version of this model, like if I didn't have these constraints on here, if this were my configural model right here, and I have no constraints, this is actually an unintended invariance constraint right here. By saying they're both 1, I'm saying that 1 is equal to 1. And I don't want that, because what if I'm wrong? So if you don't force the item's loadings to be a constant, then you don't have to worry about whether it's the same constant across groups. And to the question, yeah, if I have my factor variance at 1 in one group, what the factor variance in the other group is going to absorb that as a reference point and adjust itself higher or lower as needed, as we'll see. Okay, questions on this idea? So the logic behind not using marker loadings, let all the items loadings be estimated. That way you can tell if they need to differ across groups. So here's what happened. I have 48 parameters now. How many did I save relative to my previous model? Let me open up my handy dandy spreadsheet where I went through the trouble to catalog all of these things. Here's my comparisons, second tab. So here's where I found out whether or not I should constrain the loadings to be the same. So note the order here. The second model in my comparison is the bigger one. The configural model is the biggest one you're going to have. Relative to that, the metric model, when I've constrained all loadings, they differ in 8 parameters. So I had 9 loadings total. So if I have 9 items, that's 18 loadings across the 2 groups. If I force those 9 to be the same, that should be a savings of 9, except that I had to give 1 back to estimate the factor variance. So it works out to be a difference of 8. So my test statistic right here is 4.26 on 8 degrees of freedom. Gives me an exact p-value of 0.84. So what do I find? A non-significant test statistic is telling me what about me constraining the loadings? Okay to do that? Not okay to do that. Yeah, I didn't make it worse. So relative to my configural HO model, my metric HO model is not shorter because these are all multivariate heights. So that means those 8 extra parameters were not needed. Not worse, yes. There is no significant decrease in fit. The models fit equivalently, meaning those extra parameters didn't help. So I've made constraints that make it not worse. And so RMSEA, because it is a measure of model discrepancy per degree of freedom, as you constrain things, can actually get higher. So even though in an absolute sense we're talking about whether the model gets worse or not worse in terms of log likelihood, RMSEA can be happier because it's becoming more parsimonious. We're getting rid of the stuff we don't need. So if we go down to the solution, we will see that across the tables here, the loadings are all the same. So by the way, you guys get a chance to practice these models in your very last homework 6. And you can always tell whether or not you got your code right by checking what happens in the solution. If the constraints were put on there properly, you should see that these numbers for the loadings for the reference group are exactly the same as these numbers for the loadings in the alternative group. Otherwise, something went wrong. The covariance between item 1 and item 2's residuals still gets to be different. The means are still both fixed to 0 for identification. The intercepts are all still different. But the variances now we can compare. So the variance in the men as the alternative group is only 0.86. So it looks like men are slightly less variable in their levels of the depression trait than women. So it looks like the extent to which these items are predicted by the latent trait linearly in the CFA model is the same across groups. So the extent to which the items work as a measure of the trait looks like it's the same. I am here to tell you that in life, if you try this on your own, this is highly unlikely to happen. Perfect invariance on the first try is unlikely. This is a textbook example of simulated data. So I'm going to show you some realistic examples where this falls the heck apart in preparation for the rest of your life, because I don't want you to think that things are unique to your data that are actually far more common. What I did do in foreshadowing what comes next, though, is make a picture of the item intercepts, because that's the next layer of constraints that we're going to apply. All right, questions so far? So the next set of constraints, I'm going to go ahead and stick with the M+ code, but this is material that we haven't covered yet in the PowerPoints, but we'll forge ahead. The next one is what's known as scalar invariance. Synonym for scalar invariance is strong invariance, and that means that we are asking whether the item intercepts now can be constrained across groups. So keeping the loadings constrained and moving on to add the intercepts. So in the same way that the loadings and the factor variance are tied together, at this stage, the intercepts and the factor mean are tied together. So what's new is adding the labels to the intercept line on the alternative model for the men on the right that are being used for the women's reference group on the left. So we are saying that the intercept for item 1, which has the label I1, is now the same in women as it is in men. The intercept for item 2 is the same across groups, and so on. And in order to not also force a structural constraint, we are now allowed to estimate the factor variance, or factor mean, excuse me, goodness. So we're testing whether the intercepts are the same and whether or not the factor mean is what was responsible for any previous intercept differences. Okay, I think I changed my mind. I need a picture out of my PowerPoints because this is one of the difficult to understand topics with respect to what this constraint is. There is a big difference in thinking about what an item mean is versus what an item intercept is. So let me go back to that. What's the difference? What's the difference between an intercept and a mean? Which one is used or recommended between strong and weak? As far as you can go with constraints is recommended. So eventually we want to get to as many parameters constrained as possible. But mean versus intercept here, because on the surface, on the face of it, it looks like this is an unreasonable thing. And so what I want to make sure is you understand the logic of what we're trying to do here. Because these intercepts right here, these are actually the means of the items. Because we've identified the model such that the mean of the factor is 0, these estimated intercepts are item means. And so a lot of previous students have been confused at this step because it looks like what I'm saying is that there should be no mean differences between the groups. What do you mean the means of the items have to be the same between groups? That seems unreasonable, but that's not what I'm saying. I'm saying the intercepts have to be the same. So what's the difference? The intercept is the item outcome when theta is 0, exactly. An intercept is a conditional mean. It's the expected value when ... The when ... is the key here. So what we are saying is that if I have a man and a woman who have the same latent level of depression, they both have a factor score of 0, then their expected responses to these items should be exactly the same because they are both have the same level of depression. It's not the same thing as saying that men and women have to be the same. It's men and women at the same level of depression should have the same expected item response. So your response should depend only on your level of depression. It should not depend on your gender. There, I did it without a picture. So the purpose of me building a picture like this is to illustrate the idea of proportionality. If I look at these bars, right, in most cases, it looks like women are a little bit higher. Women have a higher mean response to most of these items, except for it looks like item 9. And what we want to know is the reason that women have a higher mean response to these items than men because women are more depressed? If it's the factor that's causing these differences, then constraining the intercepts while allowing the factor means to differ between groups shouldn't hurt the model if the factor is the reason for the differences. So we want to know if its gender is just correlated with the factor or whether there's something else that is causing mean differences between these groups besides the factor. That's what we're trying to do. So to answer that question, we add the constraints to the intercept line in the alternative group that forces the intercepts to be the same between groups, and we then are allowed to free the factor mean. Scalar invariance is where we're at here. So here's what happens. The test of scalar invariance looks like the model fits not worse. The difference between the models is summarized right here. We have a savings of 8 degrees of freedom because we had freed up 9 intercepts, but then we had to estimate the factor mean, so that's a net savings of 8. And there's a chi-square of about 12 on 8, gives me a p-value of 0.13. So in your textbook, he says that we're done. Scalar invariance holds and moves on to the next model. But as it turns out, what if I told you that one item was responsible for most of this 12? That the differences between groups that this 12 represents, that most of it was concentrated in one item. Would that change your impression of the results of this test? Yeah. So whether or not you pass the stage, whether or not it looks like the omnibus multiple degree of freedom test holds, it's a good idea to look at local misfit, to look at each individual parameter that you've constrained and make sure that there's none that need to be different whose effect is being washed out by all the others that don't. So to do that, we're going to turn to our friend, the voodoo. This thing is misaligned. 1 second here. There we go. Model modification indices. Do you remember these things? Now I call them voodoo because they are completely mathematically based suggestions for what you should do to your model and how much the chi-square test should improve if you make these suggestions. In this context, though, they're not quite as voodoo-ish because I'm not going to be looking at all the suggestions. I'm only going to look for the ones that have to do with the layer of constraints that I'm currently working with. So I'm going to use this to diagnose which potential parameters don't want to be constrained between groups. And in this result, it's telling me that the intercept for item 7 in particular, if I were to free that between groups, that my chi-square would go up by about 6, which is half of the change in chi-square relative to the previous model. So of the 8 constraints that we placed, this one is responsible for half of the misfit. It also tells you the second column here, the expected parameter change, how much the parameter would be adjusted. So what happened is that between the two groups, the new intercept that was created for item 7 was estimated at 3.711. These modification indices are telling me that it really wants the women's intercept to be 3.869 and the men's to be 3.493. So it's telling you what difference in fit would result if you free just that intercept and what the new expected intercepts would be. So I'm going to take that advice and see what happens if I loosen the constraint on just that item. So here's the results where the intercepts are forced to be equal between groups. There is the mean between the factors is estimated in the alternative men group. It looks like they are slightly lower on average, although not significantly. So the p-value in the last column is actually something that's useful for a change. because it's testing the factor mean in the men relative to the women, because 0 is the reference point for the women. So I'm going to free the intercept in one group. And here's how I'm going to do it. So I'm on page, looks like it's 9, but I'm off, so it should be 8 on your copy. So I added a little m after item 7. So I'm labeling it with a new label that is not shared by the women. So what the model is saying is that all 9 loadings are the same between groups, and therefore the factor variance is estimated. And 8 out of the 9 intercepts are the same between groups, and therefore the factor mean is estimated. So this is what's known as a partial invariance model. 8 out of 9. Are you with me? So partial as a intermediate case between non-invariance and full invariance. And here's our output. I did 2 different comparisons to describe how well this model compares to the others. One of them is to test whether or not we moved in the right direction. So relative to the model where all 9 intercepts are constrained equal between groups, how much better did we make the model by letting one of them be free for item 7? So in what I have highlighted here, I'm comparing full scalar invariance to partial scalar invariance. Are we headed in the right direction by freeing that item 7's intercept? And the answer is yes. I then compared the model with partial scalar invariance, where 8 out of 9 intercepts are constrained, back up to the metric model where none are. And it's not worse. So putting all 3 of these numbers together, 12 is the difference between the model that has none of the intercepts constrained and all of them. If I let one of them be different, 5.9 is the difference between the model that has all of them constrained and one different. And the last comparison tells me, relative to the model with none constrained, how the model with 8 out of 9 constrained does. So now it looks like the other 7 constraints are responsible only for a difference in misfit of 6, p-value of 0.5, and there's no more modification indices. So that means that we would be in good shape. So we've got all the loadings constrained between groups and 8 out of 9 intercepts. So what does this mean? If we look at the parameters then that are different, the intercept for each group. In the women, the intercept for this item 7 is 3.8, and in the men, the intercept for item 7 is 3.5. What does that tell me? So not just they're not invariant, but how are they not invariant?
I wanted to say that it means the men start lower on the trait, but I think I might not be answering that right.
You're close. So these are intercepts.
Mm-hmm.
Intercepts are always expected outcome when your predictors are 0.
Equals 0, yeah.
So when your trait score is 0, men are expected to do what?
Isn't it to be lower on the depression scale? Yeah.
To be lower on item 7.
Oh, sorry.
Mm-hmm. Yeah, so we have to be specific here because there is no scale sum score. There's either a latent trait that is supposed to be manifested in all 9 items. And then we have the individual group means for each of the individual items. Anyone curious as to what item 7 is? We go back up here. Feelings of worthlessness or guilt. So women are more likely to feel more worthless or guilty at the same latent level of depression. So there's something about that item that is resulting in group differences above and beyond their level of depression. This item shows non-invariance or differential item functioning. How many partials should you have before admitting you don't have metric invariance? So we're talking about scalar invariance at this stage. Metric is for the loadings, scalar is for the intercepts, but it's still a good question. Mathematically, you only need 1 to be invariant to hold this thing together. So another way of thinking about this is that we are testing whether or not a linking analysis would make sense. Like, what if these were 9 items that were in common between the 2 groups, and each group had other items as part of their battery that the other group didn't have? Right? If these were the 9 common items that we're using to link one group onto another, we would have to make sure that those items function the same way in how they relate to the trait. That's what we're trying to establish. And mathematically, you only need 1. Now, do I recommend linking 2 entire test batteries together on the basis of 1 item? No, that would not be a good idea. So as many as possible is how many you want to have, but if certain items need to differ between groups, that's not necessarily game over. I think to make a plausible argument that you're still measuring the same trait, a majority should be invariant, but ultimately you're going to have to make reviewers happy or have a good argument for why having items that have different parameters makes sense. So in this case, I'm not a psychologist. Oh wait, yes I am. I forgot. I have a PhD in psychology. But I'm not a clinician. But I can make some shit up right here, right? I can find some literature that says that women are more likely to feel guilty. Clinicians, can I make that up? Are you going to let me? Right? I can find some studies that say that. Even if I have to cite like Psychology Today and Oprah and shit like that, I will find some references. So if I can make an explanation as to why these things are non-invariant, but that's not such a bad thing, that can soften the blow. So yes, women are more likely to feel worthless at the same level of depression. That's what we just found. So metric invariance is for the loadings. Scalar invariance is for the intercepts. And the way that I've named these models, by the way, the first scalar model was model 3A. And then the one that we fit that allowed item 7's intercept to differ, I named that one 3B. So that's the number corresponds to like the stage of the analysis, and the letter corresponds to how many you've had to free to try and get to partial. That's the way I name things. All right. Can you guess what comes next? What other item parameters have we not talked about yet? Each item gets its own loading, its own intercept, and its own error. Yeah, error variance, residual variance. Yep. That one doesn't have a special name. So model 4 is residual variance invariance. And yes, that's as terrible as it sounds. It doesn't have a name like metric or scalar does, but people do call this strict invariance. So if you have an item that it passes the loading test, that it's weak. If it also passes the intercept test, that's strong. And if it also passes the residual variance test, that is strict. And algorithmically, we do the same thing by adding the constraints over on the residual variance line that map the alternative group's parameters onto the reference group's parameters. However, by convention, the way that we approach this is like a single elimination tournament. Because item 7's intercept was kicked out of the tournament, we're not testing the residual variance for it. So if you had an item, say, that fails at the loading stage, it doesn't participate in all the other tests by convention. There's nothing that stops you from trying it. And actually, in one of my examples, I'm going to break that rule because I have so few items that I want to try and constrain as much as possible. But by convention, you would not test the residual variance for something that has a different loading or intercept. And so that's why I have separated out item 7s as a starting point for this. There's nothing else that has to happen to the factor parameters at this stage. So when you constrain the residual variances to be the same across groups, there's nothing else that needs to be done. That's just that. So we do the same -2 log likelihood comparison relative to the partial scalar invariance model. And I have summarized the results of the comparison here, a chi-square difference on 8 degrees of freedom of 5, leading a p-value of 0.7. And if I had any suspicions that these data were fake, this result confirms them. You will never find this in your data. Residual variances being equal is unlikely. The literature is somewhat, I wouldn't say confused, but there's different perspectives on whether or not you need to care about this. So conceptually, do you guys remember what residual variance is? What does it represent? Not the factor, yes. So each item's variance in this model has been carved up into two different sources. How much of the variance is because of true differences in the latent trait, and how much is not that, right? Because we know how much there is in total, whatever's not trait gets estimated to fill in as error. So do I get super excited or concerned if the amount of not the factor variance differs across groups? It's hard to find a theoretical argument as to why that would somehow cause problems. So this is a stage where you would go ahead and test differences in residual variances across groups like we have, but if you don't have them, it's not necessarily a deal breaker the way that it is at the other stages. So that's the end of the line for measurement and variance. So in this analysis, with the exception of item 7, everything looks good for the potential to be able to compare men and women. Because the loadings were able to be constrained across groups, that means that we can talk about factor variance as representing the same idea in men and in women. Like what the factor means is the same thing because of the way the items relate to the trait. Because we could constrain 8 out of the 9 intercepts to be the same between groups, we can talk about factor mean differences as real differences. So we can compare whether or not men on average are more depressed than women on average or vice versa. So because we've passed those measurement tests, we can talk about the factor differences as if they are real, true differences and not just artifacts, which is the goal. So the rest of the stages then, here's one for residual covariance. I forgot that one. We can do the same thing. The rest of the stages after this one are for structural tests. So it works out that in this case, adding the constraint to make the residual covariance the same actually did hurt the model, so we'll leave that separate. And then we proceed on to what is known as structural invariance. So then we get to test whether or not the summary statistics of the factor scores are the same across groups. And we start with their variance, then their covariance, if there are any, and then the means. So at this stage, I'm on model 6. I'm testing whether or not the factor variance is the same between groups. The factor variance used to be free. I have constrained it back to 1. And the reason that it's constrained to 1 is because that's what it is in the reference group. So I'm making them equal. If I had identified the model such that the reference group's factor variance was supposed to be 10, then I'd have to fix this one to be 10 also. So the question is whether I need the factor variance to be different in the alternative group or whether I can let it be the same and not decrease fit. And survey says, did the model fit worse? No. So in the previous solution, the factor variance in the men was stop that, 882. The factor variance in the women reference group was 1. So the fact that the model fits not worse means that 0.88 is not different than 1. Numerically, they look different, but they're not statistically different. So this is what nope. I'll save that for later. So these are tests on the variance. The last one is the test on the means. And I actually don't even need to do a likelihood ratio test because the mean for the reference group is fixed to 0, and the mean for the alternative group is estimated. And there is the other end here. This is the standard error. This is the z-test statistic, and this is the p-value that goes with it. So that p-value was already telling me whether the mean is different than 0. So that's a walled test for the factor mean difference, which should give me the same information as a likelihood ratio test. They should converge to the same answer in asymptotically. But if I want to go through the effort to actually test it, the way that I do that is to take the factor mean on the alternative group and fix it to 0, just like it is in the reference group. And the p-value for that test is 0.27, which is not coincidentally the same p-value that I got up here. So point being, you don't actually have to do the likelihood ratio test for the factor mean. You can use the walled test result for that. If they ever were to disagree, then the likelihood ratio test is supposed to be better, but that would happen very rarely. So this test right here as to whether or not the factor mean is different across groups. What if I told you that that was the same thing as the first t-test you learned in intro stat? I just did a latent t-test. This is like latent ANOVA right here, right? Whether or not the group mean differences, whether or not there's group mean differences, nah. It's an ANOVA in latent space. So once you get to the structural level, you're on solid footing with respect to how to talk about these things. It's just that you're working with latent traits as opposed to observed variables. And here's some words. Whether or not you would need all of these words depends on whether or not this analysis is a precursor to your story or whether it is your story. So there are certain journals that would publish invariance analyses. If you have a scale that is used commonly in your research area and you want to see whether or not it works the same on a different population than which it was intended, people who read that journal may be interested in that comparison. That may become a publishable publishable product. Many years ago, I was the program chair for APA's Division 5, which is the Quantitative Methods Division, now and Qualitative Methods. And there were like 70 posters in APA at the conference that year. And I swear to God, half of them were measurement invariance of the something scale. That was a very common type of poster. So if you're in a position where you can try something like this, you would be surprised at your ability to find a home for it. I don't think that quantitative methods journals would care. I think that journals in the area in which people measure this construct would be your best bet. But it is possible to publish an invariance analysis. If what you care about is talking about, say, depression differences as a function of gender, all of this would become some sort of footnote that says, oh, by the way, we tested invariance, it was fine. Now let me tell you about the story. So I have the extended version of the write-up here, just in case you find yourself in the position of needing to report it in detail. And the write-up also refers to tables. So I would have a table that summarizes the fit of each model. That way you can explain to your readers not just what happened in terms of the hypothesis tests, but also the change, say, in CFI. So the CFI at its configural model was 0.96, and we got it all the way up to 0.97. So this is sort of supporting evidence that the constraints that you put on the model still did not really impair its fit in a practical sense. A CFI of 0.96 versus 0.97 is still a good CFI. And RMSEA, as I indicated, actually does go down because you're freeing up parameters that didn't need to be there in the first place. All right, so questions on any of this? So I told you that this is the unrealistic textbook example. I'm going to show you next time, because we're out of time. Example 7b is a former student's dissertation in which the invariance analysis quickly fell the heck apart. But you know what he did? He wrote it up and he graduated. And now he has a real job. So it's another hopeful story. It doesn't matter how terrible your analyses turn out, you will write it up and you will graduate, so long as you're willing to turn it in. So, all right, in that case, I will say goodbye for now. Office hours start now if anyone wants to chat with me. Otherwise, I'll see y'all next week. Peace out.
I'm going to stay because I want to ask that